So coming to the introduction,
So this is battery energy storage
quite
system
an economically viable energy storage option.
for
It is
energy
used
storage.
for a variety of applications ranging from energy storage for grid
So they need
applications
bidirectional
and for
to utility
applications
grid.
and electric vehicles, as you can see in the beautiful picture
So
here.
like electrical vehicle.
Now, conventionally, the three-phase isolated AC/DC conversion topology is being used, which has two conversion stages, but it suffers from low conversion efficiency.
So traditional efficiency is too low, low power density, low reliability. So we want to move to matrix converter. So this is matrix-based single stage AC/DC conversion. So only one stage. And we also need isolation.
Switches for thermal management, for the leakage energy management. However, the DAP approach does not need such a
More efficient convention straight edge.
circulate the leakage energy quite
So
well.
we only use one stage. We can increase the efficiency. So silicon
Paper will be
carbide.
discussing the
So they use the new device SiC, silicon carbide MOSFET.
what modulation strategy is effective for a 450 volt line-to-line connected converter. For such battery
So 415 voltage line to line.
so that we can have a good comparison.
So
with the
we can
other
use this for charger, electrical vehicle charger.
So
this is a topology. We have three-phase input. We need 1, 2, 3, 4, 5, 6 AC switch, bi-directional switch. And then we have transformer for isolation. And then we have rectifier.
Isolation MFT in the middle has this leakage inductor integrated into
So this
it
is
for a better power density and
we
provides
call transformer
isolation.
or
And
isolation.
also the required voltage stepped up. The secondary side, which is a conventional one, which converts the medium frequency
So we convert
and
AC
also
to DC.
ensures that a controlled sinusoidal pulse width modulation scheme is implemented.
Okay.
And
So this is the topology.
phase shift which can be controlled between them to facilitate the required power transfer. Now LAVC and the CAVC
So this is
the,
input, and we have LC filter, and then we have AC switch. So now modulation.
So the front-end matrix converter can produce a two-level voltage waveform.
So two-level voltage waveform.
And in each ES by 3, that is 1/3 of the
So we have plus and minus.
one of the 99 voltages, that is AB.
So we call it is two-level voltage waveform.
The first ES by 3 half cycle and respectively the others. Now the HB produces a 3-level waveform.
So it is not a rectifier. It is AC to
duty
DC.
cycles and phase shifts. So the duty cycle.
So we can compute the duty cycle.
That is, for the first GS by 3 period, you have a ratio of the AB line cycle, the line-to-line voltage and the VDC, whereas it switches to VDC and VDC, and then the third 1/3 of the cycle, the ratio is between VCA and VDC. So these duty cycles.
So we call this is duty cycle. So we compute the duty cycle
power requirement,
for each line phase.
denotes the shift between the midpoints of the primary and secondary voltage.
So you can see
Something
the
should be more
waveform
clear with
is
the
like
diagram
this.
here, where you can see that in each 1/3 of the switching cycles, the ratio of the pulse width on the secondary side is different based on the ratio of the switched line-to-line voltage and the VDC. Okay.
So
Now
this is a
you can
waveform.
also see the voltage across the inductor, that is the leaking
This is the
inductor, and
inductor.
the current through it, which gives
Inductor
a better
current.
understanding of the working of the modulating scheme. And this IF is nothing but 1/2 pi FSL.
So this is IL.
Inductance, which gives
So
the
inductor current.
impedance and into the voltage across the inductor. Now the average power transfer through
So this is
the
how we
consolidated
can calculate
converter can be
the
derived
total power.
by integrating the power transfer in
Power
all
transfer.
the three phases over a line frequency cycle. So this D basically shows the
And then we can calculate the duty
duty
cycle.
cycle. And there are 6 operating modes within each third of the.
So there are 6 operating modes.
The backend side APJ switching sequence.
So
is observed to be
each
the
one
for
is
third of the switching
The
cycle.
third of the switching cycle. So this is a operating
modes of operation for
mode.
the first 1/3 of the switching frequency cycle.
So this is AC/DC operation. For the details.
So I will not discuss it for brevity. So you can see that in the primary side, all the 6 of the modulation modes, only 2
So
of
we
them
have ABC 3-phase, then we have transformer, then we have DC output charger.
so that we can have a voltage imbalance at the transformer.
So this is transformer.
It is the same sequence of switching that would happen for all the 1/3 of the period, just that their durations will change so that the desired duty cycle can be achieved as a ratio of the DC side voltage and the line-to-line voltage that is being switched. Now coming to the
So now
design
we
and loss modeling, the AC/DC
design
converter has
the
three
loss
components,
model.
that is the
How much loss?
devices, transformer, and
So we have transformer
so the
loss,
MOSFET switching losses
switching loss,
by looking at the switching
conduction loss. Okay. So
over
we have transformer loss,
the
conduction loss, and the switching loss.
basically due to the switching frequency and the number of times the switching is happening.
So then-
one switching
They have to develop the loss model. How much loss
number of devices that
will happen?
also the conduction losses.
So conduction loss,
can be found in
we have RDS,
of the I square.
10 ohm resistance, and the I square.
The total semiconductor
And the switching loss.
converter can be found out by summing of the conduction and switching.
So we have conduction loss and the switching loss for the silicon carbide.
Transformers force selection.
And we have transformer loss.
Using this relation with the power
So here
transfer
is the transformer loss.
should not make the flux density go beyond its peak
So we
value.
have core loss. So we calculate transformer core loss. Core loss.
Primary, and based on the step down we can get the number of turns required for the secondary. Now
And we
these
have
are the
winding loss
that we
or
have
copper loss.
these RTC
We call copper loss or winding loss.
DC resistance.
So we have core loss, copper loss, switching loss, conduction loss. So this is core loss. This is copper loss.
Number of turns for that certain winding and then the current through it. Similarly, the core losses can be calculated with
So this is core loss.
frequency.
It is related to frequency and flux level.
And this K is a factor which
So this is a parameter Ki.
is calculated based on the segment parameters. Now for 20 kilohertz switching frequency.
So now we have 20 kilohertz switching frequency.
The total losses.
And then we calculate the losses including copper loss, core loss of the transformer.
So that we can keep the ripple cut down and
So now we have LC filter. You can see the bandwidth of the LC filter is less than 10% of the switching frequency. So we can design the LC.
Now the filter losses can be summed
So
up
the
to
total loss. Okay.
the total filter losses and the efficiency can be found.
So this is the final efficiency.
Total losses from the power transfer which is being reached from the AC side. Now in the
So
design
design guideline,
important
the silicon carbide,
that
the voltage
MOSFET
cannot offer 70% of rated value. The current cannot offer 70% of rated current.
And each wire should be chosen for a better format.
So then simulation.
The simulation results, so the simulation parameters for the 2 kilowatt converter are shown here. The AC side voltages and currents.
So this is input voltage, this is current, this is input current. So they are unity power factor. Okay. Unity power factor. Sinusoid. This is the modulation method.
Out view of the VP, VS, VL and IL. And here
This is the waveform.
view of the same so that you can see the modulation is
Modulation.
and it is the same as we did theoretically. Also the voltage ripple on the DC side is very low at 0.5% with the given
4% THD. Power factor.
And
0.97.
efficiency curves we can see that for
Efficiency 94%.
here it can go up to
So this is efficiency 94%.
5%, whereas for the non-DAB type thing we would have highest efficiency of
Because it is only one stage. So the efficiency is higher than traditional way.
due to the increased DC inductive filters conduction losses. Whereas for the conventional two-stage
This is a conventional two-stage,
efficiency
Yes,
is just
90.
over 90%.
but now we are 94. So
And this is because
4% higher than traditional two-stage.
and all the parameters are kept constant for all these three stretches.
So this is the final implemented system. H-bridge, and we have
And these are the
matrix converter, three-phase AC to DC. This is H-bridge.
parameters. And there is an impressive efficiency
2
of
kilowatt
2%.
efficiency,
4.1.
96
All these are
0.2% for full load.
4.5 kilowatt per
And the THD 4.1%.
It has short
And the power density 2.45 kilowatt per lead.
All the switching signals can be matched in case of a protection requirement. So this
So this is the
the
experimental results.
and
So you can see the current and the voltage are in phase, and all of them are sinusoidal.
These are the VP and VS primarily.
So this is current, this is voltage. We only can reach 87% like this.
Half load expander the load set one. And even here there's a THD that we are seeing.
So conclusion, so it is three-phase matrix-based AC/DC converter for charger. So we apply for charger. And it is better than traditional two-stage because we only have one stage. The efficiency is 4% higher than traditional two-stage. So the maximum efficiency 96%,
Condition is
and 2 kilowatt.
5% compared to the 93.8% of the non-DAB type and just over 90% of
And the input AC
the simulation
THD 4%, the current THD 4%, and the efficiency 92%,
2 kilowatt
and the power density 2.45 kilowatt per lead.
of 4.1% and remarkable efficiency of 96.2% with a power density of 2.45 kilowatt.
So this is IEEE Pairs
Conference.
Conference.
Very happy to discuss.
Okay, so then we can watch the next video.
Welcome back, everyone. In this video, I'm going to show you how and what.
So the first one is charger matrix converter. For a charger, this is direct matrix converter technology. We have indirect,
Electronic
we
variable
have
speed
direct.
benefit our lives in many positive ways. They are used extensively in commercial buildings, factories, and processes across many industries. However, the nature of these power converting devices results in distortion, also known as hypocrisy,
If
to
you
the
use
power supply.
rectifier, it create distortion.
This distortion can cause problems
So
with other
the rectified distortion causes problems because they create too much
variable speed applications.
input current
Energy
harmonics.
is delivered back to the power source, but instead often gets wasted in the form of heat. Yaskawa Electric is excited to introduce a new
So new
revolutionary
revolution
for
solution.
harmonic distortion and regenerative energy.
So harmonics distortion reduced, and we can bidirectional to do regeneration.
When using conventional drives, input harmonics are typical.
So input harmonics are large for traditional way, like this. So the current is like
Other
this.
equipment such as precision instruments, power source generators, and even equipment in surrounding buildings can be negatively affected.
So they will be influenced.
This
So like this
solving the
waveform.
problem of
The
harmonic
little waveform is not good.
generative energy has required the addition of extra components, such as
So they need a PMC, power factor correction, but it is very expensive.
harmonics filters.
So now we try to use matrix converter, sensory the current. Okay.
Large space is required to install
So
these
for traditional way,
extra
large
components.
space is
The
required.
Matrix Converter U1000
We need a PMC external components.
a 70% reduction in installation area.
So now we need bidirectional.
Motors normally consume energy, but sometimes
Matrix
energy
converter.
goes backwards when motor shaft is turned by an external force. For example, a lifting application such as a crane
Lifting application
consumes energy
like
when the
this.
load is lifted up.
So we need to regenerate energy
Or
when it's
regenerate
fully
when
down.
the load is lower. Another example
So
is
we
a
can
dynamo.
regenerate, return energy back to
delivered through
power
a
company.
back to a variable speed drive so that power can be measured.
So how can be measured, can be returned
Generated energy
to
is
grid.
wasted as heat in a braking resistor.
Before we use braking, but now we can return.
1000 works differently. By the Yaskawa Matrix Converter U1000 can save up to 50% of
Save
wasted
50%
energy,
energy
transferring energy to other equipment.
and provide energy to other equipment. So we can save energy.
So it is different direct matrix converter with LCD and keypad interfacing. At this time it is
So
working
this
at
waveform.
100 frequency. I'm going to turn on the
So
filter.
current
See the exact sine wave. Now
Sine
let's
wave.
change the voltage level at 100 Hz frequency. So I will select the option 1 to set the voltage level. 1 low to 8 high. Now let's change it to the highest value. So I will enter value 8 and press enter.
this is the
So
current.
voltage has been increased without incorporating DC state. You can change the voltage as well as frequency level. It uses 9 bidirectional switches
So
for its
9
voltage.
bidirectional
It is
switch.
a single state
We need
process.
a
Now let's
9
change the frequency
bidirectional
at 50
switch.
Hz and just controlling the output voltage waveform.
So we can control output
I will
waveform.
select the option 2 to set the frequency. I will change it at 50 Hz.
50
You can
hertz.
see the frequency has
So
been
this is
changed.
50 hertz.
Now let's change the voltage level at 50 Hz frequency
50
to the
hertz.
highest value. So I will select the option 8 and press enter. You can easily see the voltage peak waveform has
This
been
is
increased.
voltage.
You can also decrease the voltage waveform.
We can control, decrease
Voltage
the
level.
output
So I
level.
will enter the value 1 and press enter. You can see the voltage
We
peak
can
has been
reduce
decreased
the
now.
output voltage. Okay.
Now let's
And the
change
output
the frequency at 70 Hz with the
Now we
voltage
change the
level has
frequency.
already been set to 1. Then I will enter the value 70 and press enter to the lowest voltage
70
level.
hertz.
Now let's change the voltage level
Reduce
to this
the
value
voltage
at 70
level.
Hz. So that's it. Thank you very much.
So this is a demonstration for this direct matrix converter. Then we can watch the third video. So this is space vector modulation for matrix converter. So we discussed 5 different. Now we
Good day,
discuss
everyone.
space vector.
My name is Li Delu.
Space vector modulation
National Institute of Architectural
for
Technology.
matrix converter.
I'm really honored to have this opportunity standing here to have my presentation for my paper Space Vector
Space vector
Modulation
modulation
Strategy
strategy
and related improvement technology of matrix
of matrix
converter.
converter.
First of all, my paper is named Space Vector
Vector
Modulation Strategy
Modulation
and
Strategy
related
and the
improvement
related improvement
technology
Technology. For matrix converter.
and it consists of 5 parts. So to begin, it is introduction.
Introduction.
In this part, I will explain the reason for what I do and
So
this
motivation
research
Why
and what
do
can we
this
do
research?
for the industrial area.
for industry area.
Three-phase to
Three-phase matrix converter.
space vector modulation strategy is proposed in 1989.
1989. People
This
proposed
modulation
space
method
vector
will be
for
the
matrix
traditional
converter.
set of spatial vector paths wide modulation for
Matrix
matrix
converter.
converter control. Simple and easy to
Simple and
implement.
easy to implement.
Greatly
And can
reducing
reduce
requirements
the
of
control circuit.
The use of this method does not need to introduce low frequency harmonics
So output
in
has
the
no
output phase voltage.
low frequency
The
harmonics.
Converter voltage
And the voltage can reach 0.866, right?
maximum
Without space vector 0.56.
to
Now we
achieve
increase to
arbitrary control of
0.866
the input
to
current
increase
phase
the output
difference.
voltage.
So in the process of matrix converter industrial application, there is imbalance of industrial power supply and interference factors such as harmonics, coupled with the matrix converter input side for filtering out
So we have to use a filter
high-level harmonics and the
High-level
input
harmonics.
current.
and the
And
interference.
the second low pass filter. The input voltage of the
So we use
switch
second
matrix
order low pass
must have a
filter.
certain degree of asymmetrical harmonic distortion. Therefore, it is necessary to analyze the operating performance of the matrix converter when the input grid voltage is abnormal and adopt
So when
the
input voltage is
corresponding
abnormal,
control
unbalanced, how can
to
you deal
ensure
with
the
the problem?
normal operation of the transformer load equipment. So in this paper, the operating performance of the matrix converter under the conditions of input voltage imbalance
So input voltage
shine
imbalance.
and
How
instantaneous
can you solve this problem?
drop is analyzed respectively, and the abnormal conditions
So
have a
the
serious
unbalanced
effect
input
on the
voltage,
input-output performance,
they can
and
influence output
load
performance
increment of the
and
matrix
influence load.
converter.
So you want to compensate this
A
problem.
special vector modulation control strategy
Spatial vector modulation control strategy. So he proposed a new method
the out voltage
to
of
make the output
matrix
voltage balance,
converter as
equal
known
voltage
by
unbalanced.
compensating
output
for the
voltage
change
can be
of voltage
balanced
DC
by
voltage
using
and
this
the simulation
proposed method.
and experiment verify the correctness and
Although your
effectiveness
input is
of
unbalanced,
the
but
SVM
your
control
output is
strategy.
still balanced. So you have to propose a method.
First of all, my paper is named Space Vector
So space vector modulation
and
strategy
related improvement
and improvement technology of a matrix converter.
and it consists of 5 parts.
So now
In
second
the
part,
second part, topology
topology
and
of modulation method.
of 3-phase
What type of modulation method can you use?
is introduced.
So this is
And
matrix
a new
converter.
type of
We have filter,
change
we have unbalanced input, we have output.
the matrix
So input is unbalanced, but we hope output should be
the
balanced.
sine
So how can you
wave
propose
AC
switching strategy?
constant frequency
So this is bidirectional switch.
into a sine wave of the variable frequency amplitude and its
So output need variable frequency and a variable amplitude.
is shown in figure 1. Figure 2,
You can see we have 3 phases and then we have this method, fractional DC link.
matrix
We think that this is DC.
VSR and
And then we convert DC to AC. However, this is only imagination. In real system, we still use 9 AC
First of
switch.
all, my
So this is
paper
fractional
is
DC link.
space vector modulation strategy and related improvement technology of matrix converter. And it consists of 5 parts.
So now, third
In the
part.
third part, we will introduce the traditional matrix transformer space vector
Space
modulation
vector modulation.
strategy
So
on
traditional method and the latest method.
and the spatial vector
So this is
modulation of the
pseudo.
input
We
phase
think input
current can be performed
Convert
in
to
each
DC.
sector of the
and
space
then DC
vector
converter
positive
to AC.
hexagon, and the input phase current reference space vector I raise can be
So this is input reference, correct?
by 2 valid current vectors
So
I mu
Convert
and
two
I
different
gamma
vector.
vectors I zero
I
and set
beta,
at a certain
I
time
gamma, and I
as
beta.
shown in figure 5.
So in this figure,
The spatial vector modulation of the output line voltage
the output
can be
line
performed
voltage,
in each sector of the space vector positive hexagon
then we can
and
calculate the duty cycle
point
of the output
voltage
vector.
reference space vector U ref can be
So this is reference
synthesized
output
by
vector.
2 effective
This
voltage
is
sectors
alpha, this is beta.
vectors U alpha,
U alpha
beta,
and U beta
and 0 vectors
and the zero vector.
U0 in the sector.
So this is VSI.
As shown in Figure 8.
So figure 8.
First of all, my paper is named Space Vector Modulation Strategy and Related Improvement Technology of Matrix Converter. And it consists of 5 parts.
So now we move to the first part.
The fourth part
Opposed
is
method.
study on the mode
The previous
of
method
output
and his
pulse
method.
on space vector modulation strategy.
So his strategy.
In each spatial vector switch cycle TS, the duty cycle of the 5 vector combinations involved in the synthesis is calculated, and the control switching in some vector sequence can be used to achieve control of the matrix converter.
So they use a
The
vector
sequence
to
of the
synthesize this vector.
within each switching cycle and the
So each
position of the
switching cycle
vector
can be calculated.
vector sequence affect the switching loss and input and output waveform quality of the
Pattern influence input output waveform and also loss.
depending on the location of the zero vector in the vector sequence. It can be divided into 3 different pulse output modes. The first vector sequence within each switching cycle starts with zero vector and
So
ends
start
with zero
with zero vector
called
and ends with zero vector.
mode.
So we call pulse out mode
This
Y.
section
The first one is 0. The
analyzes
last one is 0.
this and compares the input and output waveforms and the spectrum obtained by the simulation to select the ideal pulse output mode. Figure 9 shows the output phase pulse
So this is
waves
output
of
data wave.
mode Y in sector 1 to Y, and Figure 10 shows the output phase pulse waves
This is a phase.
mode 2 in sector
This is
1
mode
to
2.
Y.
This is mode Y.
And Figure
This is
11
mode 3.
shows the output phase pulse waves of 1 to
Mode
1
3. So
sector
mode 1,
of
mode 2, mode 3.
3.
So now
Figure 12
calculation.
shows MATLAB simulation model
Space
of
vector
matrix
modulation
converter.
here.
And Figure 13
So
shows
you see
the
the
expected
simulation results.
output frequency of 30 Hz. The current waveform of the 3
Current
phase
waveform.
output phase and the spectrum
The spectrum.
phase and output current of matrix converter
Okay,
is
spectrum.
respectively adopted in 3 pulse output modes.
So mode 1, mode 2, mode 3.
Figure 14 shows the input
So this is
current
input
waveform
current.
and spectrum
Also
of
sensory
matrix converter on the 3 pulse output modes with
So
an
input
expected
sensory
output
output sensory
frequency of 30 Hz.
30 Hertz. Output.
And Figure 15 shows
So this is voltage.
high voltage.
This is voltage. You can see like this.
Spectrum matrix converter on the 3 pulse output modes with an expected output frequency
So
of
this is the
30
output
Hz.
waveform. Output voltage.
With displays hardware
30 Hz.
simulation platform as the main control unit, the experimental device matrix converter is designed. And
So this is experimental results. Previous is simulation.
Figure
This
16
is measurement or
is
experimental.
3-phase
So you can see three-phase output current
converter.
sensor. This is output line-to-line voltage. This is input current waveform. So the output is sensory, input is also sensory. They have different frequency. Input is 60 Hz. Output you can adjust your output frequency.
Input and output waveforms of
Input
matrix converter
This
is
is output.
better
This is
with mouse output mode 2.
So this is mode 2.
First of all, my paper is named Space Vector Modulation Strategy and Related Improvement Technology of
Matrix
converter. And it consists of 5 parts.
So 1, 2, 3, 4, 5.
So we get the last part conclusion.
Conclusion.
First of all, my paper is named Space Vector Modulation Strategy and Related Improvement
for matrix converter.
And it consists of 5 parts.
5 parts. 1, 2, 3, 4, 5. So
In this
conclusion.
paper, we analyze the principle of the spatial vector modulation
of the matrix converter.
Matrix converter. That is the influence of 3 different pulse output modes on the input and output performance of the matrix converter. Obtains the pulse
He finally found that mode 2 is the best one.
as the ideal
Mode 2 is the best one.
mode.
He proposed mode 1,
Through
mode 2,
simulation
and mode 3.
analysis and selects the pulse output mode 2 as the
So mode 2
pulse output
is the
mode
best one.
of spatial vector modulation strategy in the resistance load
So
experiment.
resistance load.
Thank you very much for watching my presentation and never be hesitate to contact with me by email.
So this is his
Thanks
research.
again.
And I think that he could be a master student. He used matrix converter to propose new modulation strategy. So we finished the 3 video, and now we will go back to our lecture. So So we discussed about the modulation of matrix converter. So what is the problem of matrix converter? If you use traditional way, then this is the output voltage. DC output voltage. This is like this. So what is the minimum point? This one and this one. How much? 0.5, right? 0.5. So which means your input is 22 volt. How about your DC link? Only half, 110 volt. Do you like a very low DC link? No. If your DC link is low, then means your output speed is narrow. So we have to extend the DC link voltage. So how can you increase the DC link voltage? There are several different methods. The first method we call Venturier method. What is his idea? He say you can inject third harmonics, right? If you inject third harmonics, then you can have third harmonics here. Then this one will move higher. Then you can extend your DC voltage. So this is the fundamental idea. So the researcher, his name is Bertanian, he proposed some idea. He said, if you use sinusoid, it is not good. You have to inject third harmonics. If you inject third harmonics, then you can change the voltage waveform like this, right? If your voltage waveform is like this, what is your fundamental? Your fundamental will be like this. So this point is 0.866. So you can see the idea is very simple. If you have a waveform here, then what is your fundamental? Your fundamental is like this one, right? Then how far is the peak value? 0.866. But at this point it is only 0.5, right? If you do not use this method, then your peak value is here, right? But you inject third harmonics, you change your sinusoidal waveform, then your fundamental becomes this one. So original, you have this waveform, and this is only 0.5. And then you say this is not good. So what can I do? I want to inject third harmonics. So what can I do? I change the voltage command. So I inject third harmonics. How can you inject third harmonics like this? Like this. If you inject, you put the third harmonics, then your waveform becomes this one and then this one. Then you change your waveform. So here, come like this, right? This one plus this one. And then here become this. So it becomes this waveform. What is the fundamental? Fundamental become this. So you increase the fundamental. So the fundamental becomes 0.866. So we inject third harmonics here. Third harmonics, including input third harmonics and output third harmonics. Then how much amplitude should you inject? So the Bertanian, he used mathematics to prove this is the best one. If you want to inject third harmonics, then your output should be 1/6, so 60%. Your input should be this one. Maybe this is 1.7 multiplied by 2, 3.4. So maybe only 0.3. So you put this one together, then you change your waveform like this. Then your fundamental can be increased. So the idea is quite simple. So this is the inventor's idea. And then people use his name to the modulation method we call Van Perrier method. So we can increase to 87%. However, in the line to line, the third harmonics will cancel each other. So for line to line, no third harmonics, because third harmonics automatically cancel each other. So the idea is this. If you want to increase DC bus, you have to inject the third harmonics, including input third harmonics. This is the amplitude. And the output third harmonics. Then the amplitude becomes larger. So the idea is very simple. Okay. So this is his result. He said you have to put the third harmonics, and you can calculate the amplitude of the third harmonics. Then you can use this method to obtain 0.866 maximum. So you increase your DC bus. But let later people say, if you use Bernoulli method, it is not good enough. Why? If you check the waveform, I can show you the waveform. Here. Okay. I can show you the waveform. Original Bernoulli method, it is not symmetrical. This is symmetrical. You can see this is the middle. This one and this one symmetrical. This one and this one symmetrical, right? Like a mirror. But before, it is not symmetrical. So if it is not symmetrical, then what happened? You can see this one. This is original Bernoulli. So if you use original Bernoulli, then you can see this one should be positive, right? This one should be negative, right? But in this one, everyone is negative. How about this one? Positive, right? So it is not coordinated very well. So if you want to push a car, this is a car. If you want to push a car, everyone push this way, but another one push this way. Do you think this is a good idea? No. So you can see everyone is positive, but how about this one? Negative. So the negative will reduce positive, right? And you can see here, everyone is negative. How about this one? Positive. So if you use Bernoulli, then it is not symmetric. It is not click. Click means symmetric. Then you can get this waveform. But people propose we have to be symmetric. After we do symmetric, then it is like this. You can see for positive, everyone positive. For negative, everyone negative. How about zero? Here is zero. Very clear, right? Very clear. So this is better than this. So if you can propose this idea, what can you get? A PhD. How about next one? A patent. How about next one? A product. How about next one? A house. You get money. You get a degree. You get intelligent property, right? Because this is your idea. So people propose the modified method, and then they say the second one is better than the first one. The first one is not symmetric, so it is going to be like this. But here we have this one, and then here, here we got this one. So this is not good. And if we use this one, then it is better. Okay. So now we can stop here, and we will review space vector. Okay. We will have 20 minutes break.